Welcome back to the afternoon tutorial. It's my pleasure to introduce Quentin Bertrand. Quentin serves as the, sorry, I think I have your old intro. Quentin serves as chargé de recherche at INRIA Lyon and the Université Jean Monnet in the Malice team at Laboratoire Hubert Curien. His current research centers on generative models and multi-agent learning with a broad interest in how learning algorithms can leverage and interact with synthetic data from deep generative models. Previously, he was a postdoctoral researcher at Mila under Gauthier Guidel and Simon Lacoste-Julien. He completed his PhD in the parietal team at INRIA Paris-Saclay under Joseph Salmon and Alexandra Gramfort, where he focused on the optimization and statistical aspects of high-dimensional brain signal reconstruction. Please join me in welcoming Quentin.
Okay, can you hear me well? Okay, so hi everyone. I'm thrilled to be here for this tutorial. So this is Friday afternoon, so I planned something a bit lighter. And today I will talk about cooperation of multi-agent learning. We had a lot of talk on cooperation, how to make agent cooperate this afternoon. This afternoon today. But this afternoon I want to present a slightly different perspective. Because cooperation is often seen as a feature, as a desirable property. And I also want to show the other side of cooperation, which is potential collusion of agents in everyday life. So I want this talk and tutorial to be as interactive as possible. So if you have any question, feel free to ask a question. I will try to ask a question myself. And so what I planned for this afternoon is first to show you that cooperation / collusion is very hard in multi-agent reinforcement learning. And I want to make this point by trying to make two agents cooperate in the simplest game we can think about, okay? With the simplest reinforcement learning algorithm you can think about. And I'm going to detail all the setup, what I mean by what is the simplest game we can think about, what is the simplest algorithm we can think about. I will explain all the setup in detail, and then I plan to do a bit of live coding, very, very simple live coding to show you that actually it's hard to make them cooperate. So I put the materials here on my website. You can find the material for today. But first, I'm going to present like in details what I mean by what is the simplest game I think we can think about, and what is the simplest algorithm we can think about. So, as we've seen today, there is an increasing interest in multi-agent cooperation. MSR released this autogen library to try to make agents cooperate. You have a lot of very recent work that propose protocols to have multiple agents and make them cooperate together. And I think the hope, like the promise these days, is to have a lot of agents that you can specialize on different tasks. Okay, you can take a big model and fine-tune it on a lot of different tasks, very specific tasks. And the goal is to make them interact all together. And yes, it's to make them interact and cooperate. And today, I want to show you that it's hard to make them cooperate. Okay, it's very, very hard. And this cooperation is not always a feature. Okay, it might not be a desirable property. Okay, do we have questions? Okay. So, cooperation of collusion. So imagine you want to sell some stuff on Amazon. Okay, you can sell this item or whatever other item. What are you going to do these days? Sorry? What is SGD? Oh, publicity. Yeah, okay. Publicity is a good. Okay, okay. You're gonna do marketing. You're gonna do. Okay, okay. That's true. That's true. Any other idea? Okay. How do you set this price? Yes. Set it too. Yes, exactly. So, okay, I will come to it by the end, but my point is that basically 1/3 of like largest Amazon sellers, and this was like 10 years ago, used algorithmic pricing. And how this algorithmic pricing are designed, usually you have interface from Amazon, or you can pay for additional software to have propositions. Okay, so basically, if you're ordering something from a big seller on Amazon, the price has been set using algorithmic pricing. Okay. Um, and now there's this question like, does algorithmic pricing lower prices? Like, what do you think? Like, if we all try to sell stuff on Amazon and we all use algorithmic pricing, what's going to happen? Go? I mean, I'm a bit deaf, so you will have to speak louder. Sorry. Yeah, it's going to rise the price. So we will see. We will see this, but there's been some cases. It has been documented. For instance, in Germany, like they used algorithmic pricing for to set gas price, and as you can imagine, like prices went up, and like big gas company made a lot of money out of it. So this is one example that really shows that um, they all used algorithmic pricing algorithm to set these prices, um, and there was cooperation to set these prices at a higher price than it should be. Okay, so for the consumer, obviously it's bad, it's not great. Okay, this is can be seen as a form of collusion. Okay, this cooperation of multi-agents to set high prices to maximize your reward, because your reward is just the amount of money you make. Um, and this can be seen as a form of collusion. Um, okay, from a legal point of view, it's a bit more tricky because like collusion requires explicit communication, but it can be seen as a form of like tacit collusion via learning. Okay, this cooperation stuff. And what I want to do today is simply to study this this mechanism. Like, how does this cooperation emerge um, in this type of game? So what I'm going to do is the next set of slides is simply to study, like to propose a simple setting, a minimalistic setting, to study the emergence of this cooperation collusion. Okay. Do you have any question here? No? Okay, so maybe I have a question for you. Like, what's the link with multi-agent reinforcement learning? Like, I just showed basically some basic economics/game theory facts. What's the link here? Yes. Yes, exactly, exactly. So that's exactly the question. So imagine we have two gas stations, and these are two agents, and they want to maximize their profit, which is their reward. Okay, and at each stage, they have to select the price, the sell connection, which is going to be at which price they sell the gas. Okay. Um, so here imagine you have two players, okay, two two gas stations and they can set two action. Either they set prices high, okay, or they set their price low. And the demand is going to depend on like the price of the gas, etc. But the consumption is also going to depend on, okay, did the gas station set a high price, and did gas station B set a high price as well? Okay, so basically your reward, this is multi-agent learning, but so your reward is not only going to depend on your action, but also on the action of the other players, okay, which here is kind of your opponent. And the thing is, if you both cooperate, okay, if you both, like you arrange, you make a phone call and you agree on high prices, then let's say you both get 4 million, okay? And I don't know if you're aware of this, but this is what happened in France, like for telecommunication 10 years ago. Like there was, I mean, the main telecommunication operators were convicted for collusion, okay, to set a high price. So let's say if we both agree, we both get like 4 million. If we go in some kind of price war, okay, we will only get, let's say, 2.5 million. Okay, we won't get as much money as if we agreed. And there is, of course, like this intermediate situation. Like if I set high prices or if I set low prices and and the other player, like the other gas station, set high prices, then I'm gonna get much more money than they will. So this is like a detailed example of what is called a prisoner's dilemma. Okay, so which is the simplest game we can think about. And so the question I have for you is, like, given these rules, like let's say that you are an agent, like this one, what should you do? Okay, should you set high or low price? Okay, this is Friday afternoon. Sorry? Okay, so you have only two choices, high or low price. That's a great question, that you only have like two action possible, either like high prices or low price. Okay, low price, one answer. Who thinks we should set low price? Okay, who think we should say high price? Okay, half. Okay. So the question is, the answer is it depends. Okay, if you only do one round, like if you only do one round, you should set low price. Okay, this is why it's called the prisoner's dilemma. Okay, that whatever the opponent, like the other gas station is going to choose, high or low price, I always have interest to choose a low price as well. Okay, this is like the basics of the prisoner's dilemma. This is if you do it once. If you do it multiple times, then you have other notion of equilibria that arise, okay, and always choosing a low price, which would be the equivalent of defecting in the prisoner's dilemma, is not the only equilibrium you have. So if you take this game, only one shot, then the only equilibrium is to defect all the time, to choose a low price, okay? If you repeat this game multiple times, then you have other notion of equilibrium that appears, and in particular, you start to have cooperative equilibrium, okay? So if you repeat this game, like, oh, do I set low or high price, and you do it an infinite number of times, then cooperation starts to be stable in some sense, notion of equilibrium. Okay. Is there any question on the setup? Oh. Yep. Yes. Of course. So that's an amazing question. So the question, if I can repeat, is maybe, if we're going to repeat this game multiple times, and the question is, do we have synchronizing signal to go maybe from a lower price to gently go to a higher price. Yes, well, in what I will present, there is such a cooperative signal. The question is it implicit or explicit? I guess. So you can study this in multiple settings, depending on do you allow communications between the agents. What I'm gonna propose is to have two agents that are independent in the sense that they only observe the reward and the action that has been taken. But still, you can see some form of synchronization in some sense. Do we have other questions? So yeah, the plan for today is going to be, okay, we're going to study this emergence of cooperation / collusion, potentially with this some synchronization signal in the simplest possible setting. Okay, and the question is, what is the simplest setting? And by simplest setting is, okay, what is the simplest social dilemma we can think about? Some multiple, okay, go ahead. So, you've been presented multiple social dilemma today. So what is the simplest social dilemma we're gonna study today? Just talked about it like 3 minutes ago. Prisoner's dilemma. Thanks. Okay, this is what we're gonna study, and okay, and then we have to pick a simple reinforcement learning algorithm. What's the simplest reinforcement learning algorithm you can think about? Pick one. Q-learning, exactly. We're going to do epsilon greedy Q-learning in the prisoner's dilemma. Okay, that's the plan for today. Take two agents, make them play iteratively the prisoner's dilemma. What happens if the agent's actions are guided by a Q-learning algorithm? Do they learn to cooperate or to collude? What do you think is going to happen? I take two agents, two Q-learning guided agents. Very simple, like tabular Q-learning, no fancy deep learning, no PPO, nothing. Just tabular Q-learning, two agents, and they select actions in the prisoner's dilemma iteratively. They get some rewards, which is like the money they get. Do you think they can learn to cooperate or not? No. Okay, we have a no here. Okay, interesting. What do you think? Okay, who thinks they can learn to cooperate? Okay, who thinks they cannot learn to cooperate? Okay. I think it's a bit hard. So this is the plan for today. Okay. So this is the plan for today. So how to say it? Do you want to be spoiled? So okay, maybe I'm going to spoil right now. So I think what's really it's going to depend on a lot of things. Okay, of course. If you start, if both agents start with a policy that says you should cooperate, and they cooperate, then they're going to keep cooperating. Okay. I think what's very interesting is that what's happening if you make both agents start with a policy so that they both defect. Okay. So there's a defect. What's happening? Are they going to be stuck in this defection, or are they going to learn to cooperate? I think this is what's very interesting. It's going to depend on how you initialize these agents. Okay. Okay. Maybe do we have any question on the setup? Yeah. So maybe I can detail the reward here. That's an amazing question. I wanted to write it on the board at some point. So the reward for the prisoner's dilemma, so here it was like low and high price. So standard notation for the prisoner's dilemma is cooperate or defect. So either they cooperate and set prices high together, so they have a high reward, both of them, you know, they got like the reward for cooperating, both of them. But if one of them defect and one of them cooperate, they don't get the same reward. So one of them is going to have a large reward, and the other one is going to have a low reward. Okay, so that's an excellent question. Thank you. They do not always get the same reward. Okay, if they both cooperate or if they both defect, they both get the same reward. But if one of them cooperates, I mean, if I set high prices and you set low prices, you're gonna get all the customers, and so you're gonna get all the money. So you're gonna have a larger reward than I do. Any other questions? Oh, I mean, feel free to ask. I mean, so this is like the setup. So if this is not clear, go ahead. Okay. So I think you've seen these slides multiple times today, and like how to explain reinforcement learning in one slide. So, okay, I'm going to ask it. So, who knows perfectly about reinforcement learning? Who knows about reinforcement learning? Okay, who knows? Who could implement like a Q-learning algorithm right now? Okay, 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 okay. So this might be yeah, useful. Um, so, so I'm not going to make a crash course on reinforcement learning. I mean, even myself, I'm not a huge expert in reinforcement learning, but the global idea is that you have two agents, okay, and at each step you're going to have a state, okay, which can be either your environment or for us, it's going to be what are the previous actions. And depending on this state, you're going to have to choose an action. Okay, you choose an action, and depending on this action, you receive a reward, which is going to be for us how much money I make. Okay, and to the environment, it receives this action, and it gives you like the reward and the next state. So you have these actions, these agents, they take an action, and you receive an observation. For us, it's going to be much simpler because we're going to study a super simple game. But this is like the global framework of reinforcement learning. And in reinforcement learning, there is this notion of equilibrium. You know, agents are going to be like rational in some sense, in the sense that they want to maximize their reward. And so in multi-agents RL, so if you assume that the other player is fixed, there is no incentive to change. Okay, so you basically you achieved already the maximum reward you can have. This is the form of equilibrium notion you get in reinforcement learning. So when you're doing usually Q-learning, policy gradient, etc., you try to reach this kind of algorithm, this type of equilibrium. Do you have questions on this? Not, I'm gonna go a bit further. And so, what are the forms of equilibrium in the prisoner's dilemma? Okay, if I go back to this very simple game, okay, maybe you know or not what's the equilibrium here. It's written here, but what's the notion of equilibrium? Okay, it's Nash equilibrium. What is a Nash equilibrium? Okay, go ahead. Yes. Uh, so again, I have some hearing problems, so maybe I'm going to rephrase. So what you said is that no matter what uh, the action of the opponent, you choose the best action. No, go ahead. Sorry. Uh, maybe if you, it's okay. It's a little bit. It's just I don't hear very well, so that's my bad. My bad. Sorry. Sorry. So maybe I'm just gonna explain it. So the thing is, basically, whatever your action, no matter what you pick, either cooperate or defect. So either you set prices high or low. I always have interest to choose a low price. Okay, makes sense. And so yes, so no matter what's your no matter what your action, I always have interest to defect. And so that's why it's a paradox because the only Nash equilibrium is like to defect that we both select low prices, but we would both be better in this state if we both just choose to cooperate. So if you this is what happens if you do it one shot. The thing is, if you do it iteratively, so if you repeat this prisoner's dilemma, then you start to have other notion of equilibrium that appear, and in particular cooperative equilibrium. Okay. So now we will have to choose like a setting. Okay, so we have a game. Okay, and we have maybe an algorithm. We're going to take Q-learning, epsilon greedy Q-learning, tabular Q-learning, something very, very, very simple. We still have to choose like the state space. Okay, so what do you think we should choose as a state space? Sorry, yes, pair prices, yes, like the previous prices as well. Maybe I'm going to write it as well. So we will have our policy, okay, that's going to map values from the state space. Okay, the state space, what is it? We're going to simply choose what players played as a previous iteration. Okay, so either we both played cooperate, cooperate, either we both played defect, defect, or one of us cooperated and one of us defected. Okay, so this is the state space. And it's going to go from state time action space. And what is going to be the action space? It's going to be either I cooperate, either I defect. Okay, and it's going to go and assign a value to each of these, each one of this state time action pair. And here we made a choice. This is what I want to say: is that we restricted ourselves to this one-step memory. So we only have in the state space what has been played as a previous iteration. And I think this is something very, very fundamental, which is in all this emergence of cooperation in social dilemmas, and even not in social dilemmas, in simpler environment, there is always this question of how many time step of the state space you keep in memory. Okay, and this is an active area of research, which is okay. This is a very simple game. Okay, there is no challenge here. But what if I have a larger game? So either like you can think about the coin game or the melting pot game that have been presented this morning. We have this large game where they have a huge state space. Okay, and cooperation and reward is going to have it's going to be much more delayed in these games. So you want to keep them in memory. Okay, and so one of the I would say active area of research is how to keep memory of the history in this much more complex game. All of this is just to say that I choose a very simple game, a very simple algorithm, and I choose also a very simple state space. Okay, just what has been played at the previous action. I could just stock everything. Okay, like say stack everything. Okay, I'm going to choose everything that has been played from round 1 to round like T. Okay, but I make this choice of to simplify everything because okay, in practice it might be challenging to handle everything, and in theory also it's already very complex to see what's happening there. Okay, uh, I see some confused faces in the in the audience. So do you have any questions on this? Nope. Okay. So, what do you think we can have as equilibria, as new equilibria in this iterated prisoner's dilemma? So we will have this policy, which is called always defect. Okay, so it's going to be whatever my previous state. Okay, cooperate, defect, whatever. I'm always going to choose the defect state. Okay, this is a policy, and you can show that this is a form of this is an equilibrium in a certain sense for this repeated game. Okay. So what do you think we can have as an equilibrium as well? Yes. Always cooperate. So I don't think always cooperate. I will have to check is an equilibrium. Let me think about it. So okay, yes, it's going to depend on the notion of equilibrium. So this is a trap here. I've not been super precise. So you have multiple notion of equilibrium. So usually, so previously you have this you had this notion of Nash equilibrium, and you can extend it to like repeated games. But there is an additional trick here, is that you have to start from a state, like from an initial state, which is a bit weird. Like, what is going to be this initial state? It can be like, oh, did we both cooperate? Did we both defect? And depending on this initial state, always cooperate, I think can or cannot be an equilibrium. And so that's why there is a stronger notion of equilibrium, which is that you have to be a Nash equilibrium no matter the initial state. It's called a subgame perfect equilibrium. So yes, in some sense, this is an equilibrium, but maybe not a very super robust one. So this is one form of equilibrium. One other equilibrium is like, oh, you cooperate only if you both cooperated in the previous state. This is an equilibrium. So this always cooperate is going to be, I think, an equilibrium if the initial state is cooperate. So do you have any other ideas of what type of policy can be? Yes? Sorry? Yes, exactly. So I have tit for tat here. I think tit for tat is very intriguing because regularly they host tournaments of iterative prisoner's dilemma, and people have to hand themselves an algorithm uh, that's going to try to make the maximum number of points. So we all design an algorithm for the iterated prisoner's dilemma. We submit our solution, and then we play against each other. Okay, and tit for tat has often shown to be very robust to this. So very robust, even against very complex strategies, basically. And so maybe tit for tat, for those who don't know, is simply you take the state space, take the previous state. If my opponent cooperated, so if we either both did cooperation, or if I defected and you cooperate, then I cooperate. Okay, otherwise I defect. That has been shown to be a very robust. Unfortunately, like as before, like tit for tat is not a strong equilibrium in some sense. It's not like subgame perfect. but still, it's very robust. And I think since it's not subgame perfect, also something which is very interesting that people has often tried to learn this policy because it has been shown to be to arise in a lot of social dilemma experiments, but tit for tat, the best of my knowledge is not going to be a fixed point of the Bellman equation, etc. So you're not going to be able to learn it with standard reinforcement learning techniques. Any questions on this? Okay. So I just want to mention another policy, which is a bit weird, which is called Pavlov. Who has heard of this policy before? Okay, some of you. So Pavlov or Winstell shift. And it's a bit weird, I think, from a pure reward point of view, but I think it's very linked to this synchronization signal that we were talking about at some point. The Pavlov strategy, the Pavlov policy here is simply you cooperate. If the previous state is cooperate, or defect. So basically, if we both defected as the previous round, then we synchronize to cooperate. I'm going to repeat because it's a bit weird at the beginning. So basically, Pavlov, or Winstell shift, okay, so it's everything in the name. So if you both cooperated, you keep cooperating. And if you both defected, then you cooperate as well. And this one is a strong equilibrium in some sense, in so that it's a perfect subgame equilibrium. And so it's also a fixed point of the, under some condition, of the Bellman equation. So we are going to be able to learn this policy using standard reinforcement learning techniques. Yes. Any question, interrogation on this policy? Yes? Oh, well, by strong notion of equilibrium? Yes, thanks. So I didn't want to like go into the details and stuff, but so in the single setting, the distinction of Nash equilibrium that can also be extended in the iterated setting, okay? In the sense that Nash, in the sense that the best response against a given policy is this given policy, okay? This is like the definition of Nash equilibrium. The thing is, this definition, something that I didn't talk much about is we're going to play this prisoner's dilemma in a repeated way. Okay, we're going to do one turn and another. So you need an initial state space, okay, to start your decision. Okay, we're going to use standard tabular learning, so you need this initial state space. And depending on this state space, depending on this initial state space, the policy might be a Nash equilibrium or not. So it might be optimal against itself or not. And so that's why if you say for an iterative game that a policy is a Nash, you have to specify the initial state. And my comment was, oh, what's a strong equilibrium is that no matter the state, your policy is optimal against itself. Voilà. That's the idea. Okay, amazing. Do you have other questions? Okay. Okay. So notion of equilibrium. So I talked about it a lot, but you have this kind of two notion of equilibrium, either from the game theory perspective, where you want to be optimal against yourself, or from the reinforcement learning perspective, / multi-agent reinforcement learning perspective, where you have the Bellman equations, and basically, and you're going to be aiming for a fixed point of the Bellman equation with these reinforcement learning techniques. And yes, and so basically you have to check that what you can achieve here is what you want. Okay, because like as I said, tit for tat, at least for the iterated prisoners dilemma, is not going to be an equilibrium of this multi-agent learning game. So you will not be able to learn it. And yes, so why tit for tat is not a strong equilibrium regarding your question is because imagine that you start from a state where one cooperated and one defect. Then if you play tit for tat using this initial state, then you're going to alternate or cooperate defect. So player one is start by cooperating, then defect, cooperate, defect, etc. And the other one always choose the opposite action. Okay. If you start from here, I am player one here. You defected, so my optimal action is to defect. So I choose defect. I'm player two. You just cooperated, so if I play tit for tat, my action is to cooperate as well. And this way you invert, and this you do not. This is not. Does not yield to the highest reward you can get. So that's why tit for tat is not strong equilibrium in some sense. Okay. And so now I have this question. So I told you about two equilibrium, the always defect policy and this Pavlov policy, which is if the previous state is defect or cooperate, then you cooperate. There is another one, I'm not going to talk about it, which is you cooperate only if both player cooperated at the previous step. And so toward which one of this policy do you think Q-learning is going to converge to? Yes? Sorry? Of course. Yes, it would depend on the start state. So let's say we start with both defect. At 0, the start state is like defect. What do you think is going to happen? Always defect can emerge, yes. And so what I want to show today is that basically, even if we start with an initial state that is defect, and with a policy that is always defect, with Q-learning, you can learn this cooperative Pavlov policy. Okay, this is what I want to show to you today, and like just to quickly code it up with you, just to show you that you can learn a cooperative policy even if you start with this defect state and with a always defect policy. So basically, our algorithm is going to have like multiple parameters, this initial state, as well as the initial Q values. Okay. So any questions before I go? Just to give a bit more detail on Q-learning, and we try to code it up together. Yes? So that's an excellent question. So I didn't give too much detail, but yes, you have three symmetric equilibrium for this multi-agent RL Bellman equation. So you can reach only one of these three, but that's an excellent opportunity for me to make a comment. That's why is making a multi-agent RL super hard. And even like if you look for the theory, like this is a bit, this is not trivial, but this is a bit disappointing. Okay, we're like playing the iterative prisoner's dilemma. We have a state space of size 4, 2 action, 2 player, and even in this setting, for this social dilemma, there is no theory because this is not a zero-sum game. And so it's super hard to say anything on what's going to happen in this setting. And so what's make it particularly hard is that basically you will have multiple equilibrium. Okay, so let's say you're in the Q table space, you will have like the always defect equilibrium. you will have like this Pavlov equilibrium and another one. And the thing is, all of these are equilibrium. So if you want to show that you're going to reach one of this equilibrium, you really have to track like what's going to happen and that you do not converge towards this one and your Cuba table actually reach this equilibrium. And that's why it's super hard. I mean, you can show convergence, easy convergence that your algorithm is converged to an equilibrium. But to out which one, this is super hard. Do we have other questions? Um, so, uh, so who knows about Q-learning here? Okay, I'm just gonna make a very quick recall, and then we will code it together. It's very, I think uh, it's very interesting because it's both very easy, but also very intriguing. Like what's happening? Like how do we make these agents cooperate? So how tabular Q-learning works is that you have your state space, and you're gonna have this object which is a Q table. Okay, so I erased it. So basically, the Q table is an object that aim at estimating the cumulative reward if you take this action given this state. Okay, so for us, what is it going to be? We said that we had a state space. What was the state space? It was the previous action played. Okay, so what is the set of previous action that has been played? So it's either cooperate, cooperate, either defect, defect, or cooperate, defect, defect, cooperate. Okay. So this is a state space, and our policy RQ table estimates the reward of the action that we take. It's going to be either cooperate or defect, given as the previous state. So basically, what is this? It's going to be a matrix of size 2 by 2 by 2, which is going to give you a number, okay? And basically, if the value of this matrix for the defect action given a state is higher than the value of the cooperate action for this state, then you defect. Okay, that's how you do Q-learning. And then how do you? So you choose your action. This is how you select your action. And once you have your action, then you update your Q table using this equation. This is basically saying that they're going to choose a step size. Okay, so basically, what is this? It's an update of a fixed point algorithm. Okay, if I converge, these two things are equal. So let's say that at convergence, my Q table here is going to be equal to what? To my reward plus gamma, the maximum of my Q table. Yes, and so this is tabular Q-learning. So let's do it. So again, I already asked the question, and I think I already tell you the answer. So we think it's going to collude. I put like all like the materials and solution on my website. I'm going to show it again on my laptop. So I think that's the most interesting activity is to do it together, like for me to live code right now. And as I said, all the solutions, like all the notebooks are on my website. So you can directly check the solutions if you're too tired, if you missed something. And otherwise, what I suggest, what I propose is to code it myself right now. It sounds like a plan. Do we have any questions before jumping in? Oh, okay. Okay. So let's do it. Live coding. This is always a bit intimidating. So yeah, the hub. So yes, so I put everything. So if you go on my website, You have like the material for the bootcamp you can find here. And I just created a GitHub repo with multiple notebooks that I'm gonna live code in front of you. But yes, if you have trouble to follow, you can like click on the notebook. There's all the code and the solution at the end of what's happening. Okay. So let me do this. So yeah, I think this is very intriguing because it's such a simple game, but the results are, in my opinion, non-trivial and very, very fundamental. So let's call it live coding one. Okay, so let me cheat a little bit and like import some stuff. Okay, amazing. So how are we gonna code this stuff? Okay, what do we need first? Yes? Oh, sorry, yeah, my bad. Is it better? Yeah, sorry. Yes, so okay, so what are we doing here? We have this iterated game, which is the repeated prisoner's dilemma, and it has a specific structure. Okay? The structure is given, is guided by what? What makes this problem super hard, basically? Imagine in the reward structure, I give, we both get 5 million if we cooperate and 0 for all the other choices of action. Do you think this game is hard? No, no. I mean, we have a clear signal we should cooperate. If you don't cooperate, you get 0. What makes this game hard? That it's a social dilemma. Okay, basically you could get a higher reward by defecting on the moment on the one-shot problem, but you get the higher reward for cooperation with a delay. That's why it's hard. So what makes this problem hard is the structure of the problem. So what we first need is to implement the reward. Okay, so we're gonna have this reward here, reward, and what it's gonna be? It's gonna be let me check here. So it's gonna be this type of matrix here. Okay. So I have my reward. It's a 4x4 matrix here. 0 code for defection and 1 codes for cooperation. 0 encodes defection. So you set a low price, and 1 encodes cooperation. Okay. So what I'm gonna say, what I'm saying here is that I'm choosing a specific reward parameterization. It's just something that's easy. You can easily make plots by varying this incentive to cooperate G. But what's important here is that, okay, if both agents defect, they both get 2. Okay, this is what I chose here. If we both cooperate, we get 2 times this factor G, both of us, 2 times G. And the thing is, what's happening, if I cooperate, so 1, but the other player defect, I receive only this parameter G. And you receive how much? 2 plus G. Okay? So again, my point is that it's very easy to change the game if you change the reward structure you can make the game much easier. Okay. So this is our game. What else do we need now that we have the structure of our game? Hmm. Sorry? The states? Yes. So that's an excellent point. Um, we would need a state, especially if you're implementing a complex game. You would need to implement the state space and how the state space is moving as a function of which actions the players are taking, etc. So you would have to have a very complex in some sense, set of function and functions. But since we are doing a very simple state space, in fact, this can be encoded using simply a matrix. So as I was saying, here we have this, we're going to have a Q table. And our Q table is a function that goes from the state space times the action space and that output a real number. So this is of size like 2 to the square times 2. Okay. So what we're going to do is we're simply going to create tensor of size 2 by 2 by 2, which is going to give us a number for, what's happening if the previous state is cooperate. What is basically the probability of cooperating? Okay. So yes, we can. Okay, let's do it this way. We have to select a discount factor and a step size as well. Okay, so discount factor for our reinforcement learning algorithm and a step size as well. Okay, this is the initialization. I'm gonna talk a bit more about it after. Oops. Okay, so this is the initialization for our Q values. The thing is, we want to start from a state. We want to start with a policy that's going to be always defect. Okay, so I'm going to choose after a specific policy, so TBD, choose the Q table such that the initial policy is always defect. Okay. I will talk a bit more about it after. Okay. And then what do we do? Basically, we're going to choose a given number of. So this is like the initialization. I will talk a bit more about it after. Yes, basically, we want to check that the policy is always defect. So I'm just going to copy paste this. Okay. So we have to make this test pass. It's not passing right now because everything is initialized to 0. So the question now is how to do epsilon greedy Q-learning. So how to have this, how to choose the next action given the Q table and the state, like the previous actions. What is epsilon greedy Q-learning? Yes, exactly. Thank you. Thank you. So let's say we're going to take like a random generator that, how did I do it? Yes, round of 1. Getting a number randomly between 0 and 1. And if this number is smaller than epsilon, then I return what I return the best action. So first, I'm going to have to define what is the best action and what is the best, let's call it greedy action. What is the greedy action here? So I don't know if it's super clear for everyone, but here are Q Q, and it's Q. What is it taking? It's taking the action of player one, the action of player two, and so this is a state in some sense. Okay, A1, A2, and it's taking an action. The question is, oh, if the value of defection of the action of defection is higher than the one for cooperate, then I choose to defect. Okay. This is basically the algorithm. So basically what we do is that we take this Q table. So we say, oh, Q table, we are going to select the entries corresponding to the previous state. So here what we have is that the previous state is, like, let's say, previous action yields current state. And the current state is action one, action two. Okay? So we're gonna like query our Q table at this state space, action one, action two. And then we're gonna take the argmax of this. Okay? So how is it called? Yes, there's a dot argmax here. So what is this line doing? It is selecting the greedy action. Okay? Okay, so just going to repeat it to be sure that it's clear for everyone. You have this Q table. This Q table is a matrix, a tensor of size 2 by 2 by 2. Your previous state is the action played by player one and by player two. Is that you're just going to query this Q table, this tensor, at the previous state, and you're going to query the maximum value of the Q table given the previous state. So basically, this stuff is going to return you 0 or 1, which is going to return you cooperator defect. Okay? And what is epsilon greedy Q-learning? Is simply, with probability epsilon, I return a random action or like the action with lowest probability. And with probability 1 minus epsilon, I return the action with high probability. Okay? So let's do the easy part. We're gonna do here. What if this random number is bigger than epsilon, is larger than epsilon? What do we return? We return the greedy action, which is the greedy action. And if not, we return the opposite. So the action is going to be simply 1 minus the greedy action. Okay? So this is simple implementation of epsilon greedy Q-learning. Okay? So what else do we need? Like, is it clear for everyone? Yes, okay. I see that seems to be clear. Yeah. So now we have our reward. We have the procedure to select the next action. Now, what do we do now? I think we are ready to run simply our Q-learning algorithm. for like for this simple game. Do we have questions? Yes, feel free like to ask any questions. You can ping me, send me an email if you want. Okay. Who is completely lost and wants me to do a recap so they can catch up? Okay. 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 So this is our naive implementation of epsilon graded learning. Like the point here is not to be efficient, to do batch or any kind of stuff. It's just to have something that runs. So I'm gonna do like something like, I'm gonna run it for a given number of iteration. I don't know, 10,000 iteration. And then I'm gonna do what? Uh, I'm gonna initialize everything for the player one. So Q1 is equal to 1, Q0 dot copy. What is Q2? It's gonna be, let's say, the same. Okay, so here I initialize the two player with the same Q table. And then I'm gonna do like for iteration in maxiter, like what do we do? Yes. So we are gonna have, okay, we're gonna have to initialize the state space. Let's say E1 equals 0, like effects. I initialize the state space here at defect. So this is R is 0. 0, A1, A2. And this is initialized to defect. Okay. Okay. And okay. Now we're gonna iterate over this. So we're gonna do like best action or like action for player one is gonna be simply get next action here. Okay. Of Q1, A1, A2, epsilon. What is gonna be the action for the second player? It's gonna be get next action of like, I'm just gonna replace the Q table by this one and we have to swap like the action. So like for player two, like his action or their action is A2. Okay? And then I simply have like, let's say current reward is gonna be what? It's gonna be a reward taken at action one. Or it's gonna be reward for the player one. Reward one is gonna be this. And same, the reward for player two is gonna be the same, but with the opposite. Okay? And then uh, then we apply the epsilon greedy policy update. So remember like the update for tabular Q-learning. So let's say I'm doing for the first player. What am I going to update? Okay, let me try to do some stuff. Let's say this is next action. It's going to be clearer. Next action. Okay. Um, so here's the actions are A1, A2. So what I'm going to update here in tabular Q learning, what do we update? We update Q at the state space. Okay. What is the state space? It's the previous action. Okay. And I update the entry given the previous actions and the action I just took. Okay. So I'm updating this entry for Q1. Okay. Okay, so the update might be a bit tricky, but just I think what's very important to understand is that this is the current state, and we're only going to update the entry corresponding to the current state and the action we just took. Okay, this is the essence of Q-learning. You have a lot of variations of it. You can do it by batch. You can do episodic Q-learning, but the simplest form of Q-learning is really this one. Okay, and then what is the update? Is so as I said before, it's I can show again like this. Yeah, so it's a fixed point iteration algorithm. So the update is the same value as before, plus you add the equivalent of your gradient term, like for your fixed point algorithm term. Okay, and so this is what we add. So in fact, here we're going to have this plus what? Plus alpha times what? Let's see. The reward of player one, plus gamma times what? Times this. And so we just have to compute this. Okay, so again, how do we compute this? We select the Q table, and the thing is, which entry are we going to take here? So here you update the entry corresponding to the previous state, and you take like the next state. Okay, so you take next action one, next action two, okay, and you take the max of this. Yes. Okay. And you do minus your Q table. I'm just going to copy paste this so we made no mistake, but this is really the same. Reward, next action, 1, 2, and we take the Q table, add the next state, not maxed, minus this. Okay. So do we have any question here? Nope. Okay. So this is just a simple implementation of epsilon graded learning for one agent. Now we're going to do the same for the other agent. Any idea of how to do it for the other agent? We're just going to take this update and take this symmetric of it. Okay. So we're going to swap everything. So for the other agent, we're going to swap action one, action two. We're going to swap the next actions and everything. Okay. So okay, all good. Okay, I see some nod in the audience. So let's go. So we're just gonna take the same. So as I said, you should have this as well. If you do not manage to get this, just let me know. Uh, So this is the update for the second player as well. And what we're going to do is that we're simply going to store the difference in Q value, let's say for the first player. Okay, so I'm going to maybe give some detail after on why we want this specific quantity. Okay, so this is the difference between the Q values here for cooperating minus defecting, because this is what really matters, is that in this epsilon greedy Q-learning algorithm, what really matters is the difference between these two values, okay? This is what I was saying before, but basically given a state, if the Q value for a given state for the action defect is larger than the Q value for a given state for cooperate, then you defect. Defect is your greedy action. So you're going to defect with high probability. And yes, I'm just going to like append everything. So here, it's simply some code to plot everything. So yes, I think it's even simpler if I can show you the results. So, but basically, everything I did is implemented here. And this is what you can obtain as a result for different value of exploration parameter epsilon. So maybe just a question. Who managed to access the material? Okay, everyone. Okay, perfect. Okay, so you should all have access to this. And so this is, okay, this is the plot I'm showing. I'm just, again, this is a trap. I didn't talk about the initialization of the Q values. I'm going to do it right after. But if you choose the right initialization, what happens is that what I display here, okay, maybe I can describe the results first, and then I will talk about this initialization because this is very much very crucial. So what is displayed here? So we have this Q table, okay, that we update at each iteration. At each iteration, I have a state, I choose an action, I have a reward, and I update my Q table. So for each time t, here I do like 10 to the 4 iteration, I do have a Q value, okay, a Q table. My Q table is of size 2 by 2 by 2. As I just said before, this is a lot of information. What I'm interested in is, given a state, just the difference between the Q table for cooperating in this state minus the Q table for defecting in this state. If this quantity is negative, then the greedy action is to defect. If this quantity is positive, then the greedy action is to cooperate. And here you can see multiple curves, and each curve corresponds to a previous state. So here you can see that the initialization is such that given any previous state, defect, defect, cooperate, cooperate, defect, cooperate, or cooperate, defect, no matter the previous state, I initialize my Q table such that the greedy action is to defect. You know, all the points here are negative. So the Q table for cooperating is always smaller than the Q table for defecting, no matter the state at initialization. And we're going to play a bit, and a bit, okay? Multiple times. And what's happening here? And I think this is something which is super surprising at the beginning, is that you start to see cooperation here. Okay, so the blue line is crossing the zero axis first. So what does it mean? That we cross the 0 axis. This means that as soon as we cross this line here, the greedy action is to cooperate. Okay, so as I said, each line here represents a state. So for for multiple states, defect, defect, cooperate, cooperate, like defect, cooperate, you start everything is negative, like the difference between cooperate and defect is negative. So you always start with a greedy action, which is to defect. But as you start to play, you see that for this blue curve, it's going up. And so what does this mean? It means that for this state, which is a defect state, you start to cooperate. The greedy action is to cooperate. And we were talking about synchronization at the beginning. And this is why I think it's very strange, is that you start to cooperate only if you defect, if both of you defected. So this is a bit like, in some sense, a signal for cooperation, like the implicit, the tacit signal to start to cooperate, okay? So like if the previous action is to defect, then you start cooperating. And then you start to cooperate, given that the previous state is cooperate, okay? Any question on this, maybe? On this specific graph? Any studies that look at it? For humans, so for humans, the only studies I'm aware of, I mean, I think they must have, but so there is this tournament. I talked to it at the beginning where everyone can submit their policy. But no, I'm not aware. I mean, probably there is of like results on how humans behave and when they start to cooperate. That's a great point. Probably in like economic psychology literature, there is somewhere. So the piece of work I'm most familiar with are like where humans can submit algorithms, automatic algorithms, where they select the cooperator defect action. Yes. Do you have any other questions? Like, is this graph clear for like almost everyone? So basically, this is very strange. You know, like the first time you observe this, it's weird. Like you start with always defecting all the time, and you start to cooperate, given that the previous state is defect, and then you cooperate in the cooperate state. But that's very weird. That's very weird. And you can like explore like other exploration parameter, everything. So that's it. So yes. So can you? Oh yeah. So epsilon is a choice of the algorithm. So this is your choice. Here I chose constant epsilon. Usually, I think people take decay, especially like if they're doing deep Q learning, they take decay with like something like epsilon over like the number of iteration, and then they can tune this epsilon 0. To my knowledge, is going to be very related to your step size. So basically, you have another parameter which is your steps as alpha, and this like the relation between both of them is very tricky, and it feels that you cannot need the same of the order of magnitude of both, at least for this to happen. But yeah, basically that's a Q learning epsilon greedy Q learning algorithm, hyperparameter. Any other questions? Okay. So just to conclude, I'm just going to talk quickly about the initialization, because this is the only thing I didn't talk about yet. So basically, you have to select a very specific initialization, because as I said before, like always defect, it's a fixed point of the Bellman equation. So if you initialize your Q table at the optimal Q values, then there is no way you can move from this fixed point. Okay, you're at the fixed point and you're applying fixed point iterations. You're just going to stay there. Okay. But I think this is the trick here is that you initialize your Q table so that the greedy policy is always to defect. But if you initialize them in an optimistic enough way, then you can see this emergence of cooperation. And when you start to think about it, it makes a lot of sense. But yeah, that's really like the trick and the salt of this of all this work is to have a good enough, an optimistic enough initialization such that this work. Maybe I can like just say a quick word on it, and then continue the presentation. So this is this trick that, you start at time t equals 0, okay? And at this time, you have this, you have two Q values. You have your Q value, let's say, for the defect state for cooperating, and the Q value for the defect state for defecting, okay? Your greedy action is to defect. Both players play defect, so you're only going to update this Q entry, okay? But what's happening is that the optimal Q value can be there, okay? Like your convergence Q value. So the greedy action is to defect. You choose defect. It's the same for your opponent. So you both play defect. You only update this entry of the Q table. And you know that the optimal value, like the value for the fixed point, is this Q table. So basically, you're going to converge towards this value, okay? But the thing is, what's happening when you hit this value? So you're in the defect state. The greedy action is to defect, so you defect. Your opponent does the same stuff. You do it again and again. So you're slowly converging towards your optimal Q table that is here. So here you can see that I chose this at initialization smartly so that it's larger than this value, okay? So I do it. I update my Q entry. I only update this Q entry. And then I start to cross this value. And when I cross here, basically the Q entry for cooperating is larger than the Q entry for defecting. So that's the trick in some sense. So once you cross here, you start to cooperate in this defect state. And that's why you have this weird transition. Okay, maybe is there one remaining question here? I can take one or two questions here, and then I will continue. I will resume the presentation. Yes? So that's an excellent question. So maybe I can repeat the question. So the question is basically epsilon is larger here. So you have more exploration. And maybe like one natural idea is to say, oh, maybe if I explore more, I will explore the non-greedy action, which is to cooperate. And then I might start to converge faster. Or basically what's happening with larger epsilon, there is this weird stuff. So first, I mean, that's an excellent question. I don't think I have all the answer to these questions. Maybe I can just comment on it, which is I think that the choice of epsilon is very related to your step size. Basically, it's epsilon. If your noise level is super large, you need small step size to kind of control the stochasticity in your algorithm. And so here, everything is done for a fixed step size alpha. So as I said, epsilon should be chosen in accordance to your, so the exploration parameters should be chosen in accordance to your step size, which is not the case here. So I think that's um, the first answer. And then, yes, I wanted to mention something else. I don't. Okay, I just forgot. But yes, I think this is one. And then what's happening? Yes. So basically, we have these two agents. They are playing against each other, but there is no decrease in the stochasticity. So there is always this epsilon greedy action. So usually, as I said, like the standard practice is to choose noise level that decrease linearly. You know, like 1/t, something like this, which is not the case here. So there will always be some remaining noise. So noise never vanish, and you can have basically this process will never converge if I don't make the noise vanish to zero. So that's why we may observe some strange behavior. Um, but my point would be that it's super hard to analyze in practice to say anything, to analyze in theory, I mean, to say anything on the behavior of this agent. So we started with like a fixed step size epsilon. I don't know if it answers all your questions. Yes. Um, do we have other questions? Okay. So if not, I will resume the presentation. So uh, some speaker talked about it like extensively this morning. But you can also make this self-play assumption, which is very common and it's very useful in reinforcement learning because it makes things simpler. So you play against yourself. And so you can also make like the theoretical analysis like this by supposing that you play against yourself in some senses. It makes things like, I mean, this is a very strong hypothesis. You can relax it. What I just show you, what without self-play, so the emergence of cooperation / collusion without any form, without any self-play. But self-play makes it easier. You can relax. Basically, you can make very technical assumptions to relax the self-play hypothesis. So what does it mean? Self-play is that basically your Q value and the Q value of your opponent are the same. And to relax this type of hypothesis, you basically have to control and say that, oh, they do not move too far the one from the other. Okay. My point is, this is a very strong assumption. This can be relaxed at the price of a lot of technicality, which I'm not going to present today. So this is a common assumption in multi-agent reinforcement learning. Multiple speakers talked about it today. The idea you play against yourself. So the core idea is that the Q table is the same. So the greedy action is the same, but you still have some randomness because you only select the greedy action with probability 1 minus epsilon. So they do not choose exactly the same action. And it's maybe I just want to mention some like older work, where they say it was hard to find cooperation. Like this has been studied empirically extensively, and people always thought that cooperation was not possible, especially because it's super hard. Basically, if you take, I just gave you an initialization that works, but if you take a random initialization, there is no way that your agents are going to cooperate. There is no way, okay? At least in this game, in this cooperative competitive game. And so that's why like people in the literature, at least empirically, observe that almost no cooperation emerged. And I think that's very important because like as I was mentioning at the beginning, like today with like LLM agents, we have this promise that, oh, we're going to train a lot of agents that are going to be specialized in some different tasks, and we're going to make them cooperate. And I have to say that each time I see someone presenting these deep reinforcement learning empirical results, I am impressed because it's so hard to make it work in practice. Like deep reinforcement learning, it's very hard. And especially, I just show you that on the simplest possible game, 2-player, 2 agents, state of size 4, it's super hard to see any form of cooperation. And so when you take like much harder games, which delayed rewards, larger state space, I think it's going to require to be very, very smart to make them cooperate. That's my point. And so what we did in this work is that we basically analyze things, try to analyze things in this very, very simplified setup. But as I said, it's a non-zero-sum game. It's multi-agent reinforcement learning. There are no results, basically. And so what we show is that in this very, very simple setting, you can show that this cooperation is going to emerge. You can prove what we just saw here. So here, like these multiple phases. So this is just a close-up on the graph I just showed you. You can really truly show this behavior that you will move from this always defect policy. Slowly, you will have a shift here. And so you will move toward what is called the slow shift policy, which is you cooperate only if the previous state is defect. And finally, you will start also to cooperate if the previous state is cooperate. And so may looks naive, but this is highly non-trivial. And I truly believe that cooperation is super hard, and it's gonna require to properly understand what's happening under the hood to make it happen. There's a lot of people in Gautier's group, especially in Aaron Corville's group, trying to make cooperation work in larger environments. And yes, I think that we are very not there yet, especially for a bit more complex game. So I will not go like in the detail of the theory. Yes, these results can extend to like deep learning experiments. I just proposed a lab with PPO. And maybe, yes, if I can just conclude. So my point here was to show you that cooperation/collusion can emerge, even if you start from a defect initial state, even if you start from an always defect policy, agents can learn to cooperate. Okay, it's going to require some very specific assumption. On the initialization, you have to be optimistic enough to have this convergence. You have, in theory, to make this self-play assumption, which is very equivalent to this shared belief hypothesis that has been extensively discussed this morning. So you can have to have shared, not values, but belief at least. You mentioned, but for this cooperative policy to exist, you also need strong reward for cooperation. And again, this is limited to very, very, very simple environment. But yes, I just wanted to talk a bit about future work because I think that this is very exciting. So the question is like, what about more complex game like dilemmas? Like if you had more players, what's happening? You know, you have more players. What's happening to this probability of cooperation? So basically, there are extensions in economy to like this kind of iterative prisoner's dilemma with more players. You have multiple players. They have to set a price. What happens if you have more action? Like, is the probability of cooperation going to vanish as the number of player action? I don't know. What about if you have a larger state space? You know, like you have this type of games. Basically, these are cooperative, competitive games in this type of environment. You have like apple growing at a certain rates, and you have to not eat all the apple so that everyone can survive. But what's happening there is that first, the state space is huge, and then the delay for the reward is huge as well. So a one-step memory algorithm. So if you only keep in memory the previous state it's never going to work for this type of algorithm. So you have to store a bunch of states, basically like the 10, 100 previous states, but it's too big. Okay, so very active area of research is how to find meaningful representation for the state space so that you can compress it and get information from it. Okay, I think this is a very important question, and we are very much not there yet, in my opinion. And yes, so the whole goal is how to cooperate in more complex environments. I mean, there was some presentation this morning on super complex, like 3D games, like Portal, etc. I think there is a range of complexity going from this like toy, iterative prisoner's dilemma to Portal or more complex game. And I think we will need to study what's happening in this, let's say, game of intermediate complexity if we want to understand what's happening after. Okay, thank you. Okay.
Any questions to Quentin?
Yeah.
You discussed the idea of the importance of the initialization, which
Yes.
is much easier and tractable in tabular environments.
Yes. Great question.
How do we realize the same for more complex environments and agents?
Thank you. Thank you for the question. So what we did is that you can choose Q tables and do supervised learning before, like for the initialization. So you learn your network to match the Q tables you want before running the algorithm. So this is one way to initialize. I don't know if it's clear, but yeah.
And with this, can we still do like this optimistic initialization?
Yes, exactly. So yes. So this basically your network is also going to be a function that takes action 1, action 2, and that output a value for cooperator defect. And so what we did is that we pre-train this to match values that we know are optimistic. So you say, so you learn your parameters theta 0 such that this quantity, maybe you can see, maybe I can write it here. So we pre-train the network. So the question is, how do we get optimistic Q tables initialization for deep Q learning? So I know the value of the Q tables that are optimistic, and I use it to do supervised learning before to initialize my network.
Last follow-up.
Yes.
Do you think if the effect of the initialization the same if we use Q learning compared to a policy gradient algorithm, for example?
That's a great question as well. So I tried a lot of stuff. So from what I remember, it was harder to get cooperation with policy gradient style algorithm. I don't remember exactly why, and I have to do it. That's my answer. Sorry.
Thank you.
Hi, I'm just wondering, so the setup here of sort of starting with like the most simple case, usually that's in a context where like, well, if it doesn't even work in the simple case, or how does that translate to the more complex case? And in this case, it seems like the more complex case is having LLM agents doing lots of stuff, but that almost feels like I'm wondering what of the intuition that you've built up today do you think transfers over when you have AI agents that are leaning heavily on LLMs to do the communication and where there's maybe not like a explicit value function and et cetera, et cetera. Like what if this simple case has implications on the complex case?
So yeah, so thanks a lot for the question. So yes, there is a whole range of game from like this super simple case to like make LLM agent cooperate. So I would say the insight we have from this is try to be optimistic with the Q table. So this transfer to like deep Q learning transfer, quote unquote. Okay, this is always super hard to make this multi-agent deep Q learning experiment. I don't think we are there yet to give like any insight on how to make LLM agent cooperate. So sorry. Like
but there's some. So I mean, people worked on DeepRL for a while, and that's where sort of this was heading. Like people like Joel Leibel looked at social dilemmas, and there was this sort of trying to embed that game structure into DeepRL agents.
Yes.
Now with LLMs, it seems like we now have access to this deep prior that involves, you know, priors that humans have about the way that they communicate and cooperate with each other. And is that going to just completely bypass this more technical work, or?
So
I don't know if it's a well-formed question.
No, I think it's a fascinating question, but so yes, my point. How do I say this? Okay, the thing is, we want the agents to cooperate, and so what's currently done, like with Labo, as you mentioned, is there's a whole team at DeepMind working on how to make agents, deep Q learning agents, cooperate in social dilemmas. And from what I understand, like this, the core idea is, oh, how can I come up with a new algorithm? And in my opinion, it's very hard to make them cooperate without any form of communication / synchronization, as you mentioned at the beginning. So this is maybe my insight, quote unquote. So just I don't see, I mean, except in this case, I don't see currently algorithm where cooperation emerge without this type of synchronization or at least communication between the agents. And maybe this is also one of the insights that we have here. Like you need some form of cooperation, and yeah, maybe this is one insight. Like you need some kind of synchronization between the agents, synchronization signal. So yes, maybe it's going to be like one insight. It's going to be hard to make things work in a fully decentralized setting. Maybe one hope I have is that for multi-agents LLM, you may not need to like learn the agents on the fly, because this is a very specific setting where you have two agents and they learn on the fly. For LLM, maybe you can fine-tune everyone and then just, quote unquote, to make the agent interact, which might be easier than making them also learn on the fly. I don't know if it answers your question.
Thanks. Thank you. Anyone? All right. Quentin, that was wonderful. Thank you for that passionate lecture.
Thank you. Thank you.